I think perhaps we're ready to begin. What I want to do today is to talk about some research work in the general area of insect communications that has been carried on by a large group of people. Dr. Jerry Kuhn in entomology, Dr. Joe Biles, John Muchmore, Wayne Rowley on this campus, Bob O'Connell at Rockefeller University in New York, and very recently Morton Barossa in Beltsville, Maryland. So it's a large group of people dealing with many facets of the problem. All of these people, including myself, working in this area for very different reasons, as we're looking at quite different things, but I think all of us have results and ideas that contribute to the solution of a very general problem. Now, pheromones is perhaps a term that some of you have not encountered. Pheromones are compounds that are used in communication. Now, this varies widely with species. Insects use them, fish use them, mammals use them for certain. Insects use airborne chemicals. Fish, of course, have waterborne chemicals. In the case of mammals, they can be primarily airborne, although sometimes they're deposited on solid substances. I think that if you think about it a little while, you realize that pheromones do have an effect on you. The perfume industry is a potent testimony to the manner in which this has been employed in one usage. But more importantly, I think that if you think for a little while, you realize that odor has, to human beings, a very emotional kind of content. That is, a single odor may cause you to recall a whole period of experience. Cumarin, which is the odor of new mown hay, for example, might recall to you a whole summer spent in the country or something like this. It's also important to realize that in your perception of the odor, that you use a different kind of brain input than you do with your tactile sense or your visual sense or your hearing sense. When you look at something, you have a very quick response to it that is filtered through your intellect. That is, if you see an optical illusion, you perhaps recognize it as an optical illusion, not because of what your eyes tell you, but because of the processing of that information by the brain. And in fact, if you play tricks on yourself, you will try to see sensible things in nonsense situations. This is because the intellect is filtering it. In the case of odors, the intellect does not filter it. There's a very direct input, and this has evolutionary significance. The odor perception came in very, very early and has been little transformed in various species. There are various ways of making this point, but one that I think makes it very directly is this. Take the concept of beautiful versus the concept of ugly. Several men in the room. A man, I think, will understand that he might love an ugly woman because he could perceive intellectually other virtues. But I cannot conceive of any man loving a woman that he perceived to have a stench about her. Now, what a stench is. What a stench is varies from society to society. But if you perceive a stench, I think that you cannot intellectually overcome that. There is no way to rationalize your way out of the stench. Now, let me start again. Actually, I'm going to give the lecture twice today. I think for those of you who are not chemists, it will be a little easier. What I'm going to do is sort of go through it once very quickly using the magnificent chalkboard we have available to us today. And sort of hit the highlights and tell you what to look for in the slides. Now, my particular entree to this problem of pheromones is based on the fact that I'm too stupid to do what I want to. What I want to do is to understand insect brains, which look like this to me. There is a receptor side of the brain, and there is a motor response side of the brain. data processing side of the brain, and there's an information storage part of the brain. Now, the insect is born with everything he ever needs to know, and consequently, this information storage is chemical. The programs are all there, the behavioral programs. Once they are triggered, he goes automatically about his response. Now, what I really want to study is information storage and data processing. But I'm too dumb to know how to do that. So I've decided to come over on the other side, the receptor side of the brain, because the input here is chemical, and that makes it nice for me. And to try to learn about the programs that go in on the receptor side of the brain and activate the data processing part of the brain. The motor response sides of brains people know something about. And in fact, the pesticide industry as we know it today is very largely dependent on interrupting the brain process on this side. Now, let's think a little bit about what's going on by way of getting chemicals from one insect to another and getting them on this receptor site and producing the signal that activates the brain programs. The species we'll be talking about are Lepidoptera, little moths. Think of that as a female moth. Setting head to wind and secreting a chemical from the tip of her abdomen. As the chemical comes out, it will form into a conical pattern downwind, and downwind there will be a male moth minding his own business when suddenly his antennae will begin to quiver, and he will notice that there are interesting things upwind. Now, what he will do is to turn and fly upwind and find the female, and it's a very efficient scheme. The Hellstrom Chronicle, which is a very interesting movie, said that Luna moths operate over 22 miles. I cannot find that in the literature myself, but I can find claims up to 7 miles, and certainly these can operate over quite long distances. In the case of the corn borer, we know that almost any place you put an insect in central Iowa, the female will find males. So if there's a female who's in the mood in the wild, there will, in a 12-hour period, be a male to mate with. So it's a very efficient system. Now, the other thing that's interesting about this is that the concentration of the compound she secretes is almost vanishingly small. We know that the male moth is active at concentrations less than 100 molecules per cc, which is by any reasonable standard pure air. And that means that the male moth is active to probably single molecules, and that the response of the male antenna is very much like the response of the human eye to single quanta. The human eye has a threshold of about 3 to 5 light packets or quanta, and is thereafter sensitive to individual quanta. So the insect is as sensitive to molecules of this compound as the human eye is to light, and that's very sensitive indeed. The compound secreted by the female produces two kinds of behavior. One I've mentioned already, that is flight orientation. And the second is precopulatory behavior. The male moth in precopulatory behavior waves his wings wildly over his head, falls down, he can no longer fly, extends a little organ on the tip of the abdomen, and is ready for action. So there are two behaviors then, flight orientation or attraction and precopulatory behavior induced by the same compound but in different concentrations. Still minute, still far too low for any man-made device to detect. Now, the obvious thing for the chemist to do then is to come in and find out what is this compound. And how do you do that? Well, you aren't going to sit out there and collect the stuff downwind from female moths. So you go to your friendly corn borer laboratory in Ankeny and ask for 250,000 virgin females. And then lots of people sit around and clip the tips off these female abdomen, and then you extract this and put it into a suitable container after purification. After all of this, you have a container about that high and about that wide. It's a melting point capillary, and actual size is about the size of that line. And the container is filled from the bottom up to about that point, which means that from 250,000 female moths, you have just about enough stuff to look at. Now, this is the right stuff, though, because the males go absolutely insane. At this stage, you make use of a kind of instrument that chemists are very partial to, called a gas chromatograph. And what it is a means of separating compounds, and the way it appears to the chemist is a strip chart recorder paper coming out with little tracings on it. And the life of the chemist these days is very largely devoted to understanding what things like this mean. And one of the things that bother you a great deal is that this very active material from the females is not pure. It is, in fact, a mixture of about 50 compounds, and that's bad news. Well, you have all of these compounds coming off your gas chromatograph, and you want to know which one is the pheromone. And you feel sort of silly, but when nobody's around the lab, you've got a male corn borer moth by the wings, and sort of sidle up to the output of your gas chromatograph and run the sample through. And then you get a very real disappointment, because what happens is that the male goes wild at a point where the chromatograph has come down to the baseline. That is, in this stuff which you work so hard to get, there is not enough of it, of the active component, to see by the most sensitive detector that we have routinely available to us. Well, after you get over that disappointment, you come back and look at the compounds on either side where this appears, and you learn something about what they are, and you find that they are straight-chain compounds. That is, they are things with one carbon after another. They're appropriate component of hydrogens. And you have an ester function on one end. We'll say what an ester function is later. And then you have one double bond. That means there are two bonds instead of one between the carbon. And the carbon chain always has 14 carbons. So those are the three things that you learn. Now, there are quite a few carbon chains that have these features. I suppose 50 or 60 all told. And it's not too much for the chemist to make these, and so the way you decide to go at this is to find out, by making the individual possibilities, all of them, where the double bond is. Okay, you do that, and what you learn is this. Compound which has an acetate. This is just a grouping which is the component of the acid in vinegar, acetic acid, followed by carbons. That is, there is a chain of 9, 10 carbons. Then there's the double bond, and then there is an additional 2 carbons on the end. Now, the double bond is a critical thing, and there are two kinds of double bond in this position. One has the hydrogens on the same side, and is known as the Z or cis form, and there is a second which has the hydrogens on opposite sides and is known as the E or trans form. These are quite different compounds and will form a major portion of our story. So this is the compound then that the female is secreting, and This is true not only for the European corn borer, which is one moth we'll be interested in, but the red-banded leaf roller as well. Actually, there is at least one more species that is said to use this compound. Okay, this is then the chemical identity of the material that the female secretes. Now, you want to be sure you have the right stuff, so you're ready to do some bioassay. You're going to talk to the male moths now. Then you realize that you have a problem. Very quickly, you can show that this compound in the laboratory elicits pre-copulatory behavior in males if the male has been exposed to normal light-dark cycles, that's normal circadian cycles of light. And secondly, if you cool it 10 degrees. Now that wasn't totally obvious right from the beginning. And after a while it makes sort of sense. You wonder how these two insects are staying out of each other's hair in the Iowa fields, and one of the answers is that the European corn borer does not fly as early in the evening as the red-banded leaf roller does. Red-banded leaf roller flies as soon as the sun goes down about 6 o'clock. The corn borer waits until 10 o'clock, and the clue was that there's about a 10-degree temperature drop between 6 and 10 in Iowa in July and August when these moths fly. Okay, that was one of the problems. The other problem comes that to test flight orientation, you have to go out in the field and do this. You cannot do it in the laboratory. And that means that you have very limited times to do it because the moths fly only in certain times of the year. And in fact, there are only 2 flights per summer for the European corn borer. So you have to get out in the summer at just the right time for your tests. The other thing is a concentration effect, which was not realized, and that is that if you put this out in too high a concentration, the corn borer males go into pre-copulatory behavior a half mile from the trap, and they don't catch anything. That's one thing. So there are many problems with this kind of field test work in biology. Okay, we'll come back to that and I'll show you some pictures of how we trap those things and some of the problems with slides. Now let me talk a little bit more about what happens on the insect, because this is a very interesting area. The antenna of the insect is a marvelous thing. I'll show you some beautiful slides taken here at Iowa State. On the top side, it has little plate-like devices of unknown use coming out sort of like this. And periodically, off the main antenna, there will be a little finger-like projection. And on the underside of the antenna, it's just wonderland in terms of the organs that are involved, most of them of unknown functions. But in our case, it's these little organelles on the top of the antenna that really are responsible for the pheromone action. Now these little organelles look sort of like a finger sticking up out of a pit. And in fact, if you take a cross-sectional view of one of these, you see little ports in the side, and inside you see projections of nerve cell fibers. At the base of the little organelle are 4 nerve cells, 2 of which fire when you produce the flight orientation behavior. And I should say how this is done. The common way of monitoring messages from antenna are to monitor at the base of the antenna where it meets the brain. Now this is sort of like trying to understand what goes on Elm Street by monitoring the traffic on Lincoln Way. You know, there is perhaps some relationship, but it's not obvious, and it can be unscrambled only with a detailed understanding. In this case, it's impossible. The whole electroantennogram, or EAG, as these measurements are called, just don't give you the information you need. But when you can go in at the base of this cell, at the base of this organelle, with another probe elsewhere on the antenna for reference, and a microvoltmeter to measure signals, Then you can tell when individual nerve cells fire. You can distinguish the two cells by actually distinguishing their pulse patterns. And this is the work that Bob O'Connell does at Rockefeller. He's the only one in the world that seems to be able to do it right now. He takes an anesthetized moth and puts in a microprobe. This little organelle can be seen under 100-fold magnification, but to get a good look at it, you need 3,000-fold magnification. So getting a microprobe in at the base of that, in contact with these cells with a pressure that does not break the cell wall, is quite a trick. You put it in partway with a micromanipulator with a screw on it, but the final adjustment must be made by hand to the sense of touch, and that is why only Bob O'Connell can do it. He's not been able to describe that touch to anyone else. Okay, so we can monitor then these individual nerve cells, and we see actually the signal that the nerve cells send to the brain. Now, the cis isomer or Z isomer of that chemical compound I mentioned fires both of these cells. So Z fires both A and B. The E isomer, the unnatural isomer, fires only A, which is a very interesting thing. So the compound, which has no overt physiological behavior, in fact sends a recognizable signal to the brain. And one of the things that the chemist can do is to synthesize molecules that are non-natural compounds and see what the insect how the insect responds to these. And we can tell a clean-cut brain signal from, in fact, a noise signal. So some progress is being made there. If Bob O'Connell were able to do more of these measurements, progress would be faster, but even his patience has some limits. Now, let's look a little bit closer at this. I think maybe we'll turn to the slides now. This is one of the moths that we deal with. I think this is a red-banded leaf roller, but I'm sort of casual about the biology. This, I think, is an oblique-banded leaf roller, which also is a common Iowa moth. And this is the one that we're really interested in, the European corn borer. The European corn borer does not eat in the moth stage. The fact that he's on the corn borer leaf had to do with political reasons and fundraising, not with what the moth actually eats. His mouth parts are ineffective and do not function. The moth is born with all of the energy and resources he will ever get. So the moth stage is not a commercial test. Now, if you take this moth and expose him to an infinitesimal concentration of the Z isomer of this compound, he goes into wild ecstasy, fluttering his wings and extending this little organ on the tip of the abdomen. The thing in the upper left corner is just a capillary. In fact, a favorite trick is to try to get visitors to rinse out this capillary with chloroform to get rid of the pheromone. And no matter how long or how hard they try, you never get rid of it. It's always there. The moth always goes absolutely into frenzy. Now, this is 100-fold magnification of the top side of the antenna, showing these little plates that I mentioned. And you can see up here one example of the little organelle where the pheromone goes on. And this is the underside of the antenna with lots of long hairs. You can see a honeycomb-like structure in the antenna. We have some close-up views of this. These are all organs of unknown purpose. I think these little organs, like this one and this one, are actually temperature sensors and are in fact related to the infrared detectors of rattlesnakes Many people don't realize that rattlesnakes strike using an infrared detector. That is, they base their strike on heat, not on vision or smell. So it's an infrared detector, which we do not have at all. In fact, you can do experiments with rattlesnakes covering up their eyes and blocking their nasal passages, and they will still strike. But you can take a rattlesnake that is in no way impaired as far as his senses and put in a warm light bulb covered with a little soft cloth, and he will strike the light bulb. So he's striking at the infrared source. And certainly these insects are sensitive to light and to heat, and they have to have monitoring devices. They are somewhere on this antenna. These are more of the organs. I don't know what this thing is. It looks like an ear of corn down here, but presumably the insect does. I suspect each of these is responsible for the detection either of heat or light or particular chemical compounds. The insect actually probably conveys and receives a great deal of information chemically. Still some more views with a little better relief. It is in fact an incredible thing, this antenna. It is the best small detector that I have ever come into contact with. And it makes things like the manned and unmanned space flight seem so prosaic. This little insect can get so much information with so little volume, weight, and space. This is a blow-up of the organ that the pheromone goes on. And now I'll show you some cross sections on the antenna. These are the cross sections. You can see the little ports into the side of this stalk. You can see the nerve cell projections coming up the stalk. I suspect that the real interesting thing that we have next to do is to get at what is in this clear liquid inside the stalk, which is probably a protein-containing solution. And somewhere with the pheromone coming in here, it probably forms a protein pheromone complex, which then becomes a catalyst for further chemistry. These are the core nerve cells at the base of the stalk. Two of these, of course we don't know which two at the moment, are responsible for the signals which go to the brain in the pheromone communication system. Now, I pointed out that chemists can make these things. For those of you who are not chemists, I want to make only one point. We start with something that has a triple bond, or at one stage we have something that has a triple bond in this position. We can reduce that with hydrogen and a palladium on carbon catalyst to put in two hydrogens on the same side. That is to make the Z isomer of the compound. But always this has a few percent, about 5 to 7% of the opposite compound, that is the E isomer. Now, in the early tests on these insect systems, people said, well, you know, trans can't hurt anything, cis is a pheromone anyway, so they use those mixtures in the tests, and that has important consequences. One can also make the trans isomer from the same acetylene, that is, this is the E or trans isomer. This is the compound with the 14 carbons and is presumably the true pheromone. This compound, remember, fires both cell A and B. This compound fires only cell A, although it doesn't obviously have a biological function. One of the things that we found that really has led to major advances was that the trans isomer, if you have lots of it, inhibits the attraction of the cis isomer for the insect. That is, this is an inhibitor, and that's a very wild observation. In fact, it has some practical overtones, as we'll see in a little while, and it was a very important clue to us, although we were too dense to see it. I have here some pictures of molecular models of the cis and trans isomers. This is the cis or Z isomer. These are the two hydrogens on the same side. And the point I want to make here is that there's a hook in the chain because of that Z double bond. The trans isomer has no such hook. It can extend into an almost perfectly linear molecule. And I think that shape difference is probably very important in the chemistry of these little compounds. Now this is the kind of trap that we used last year, and that's Dr. Jerome Clune, who was the entomologist in this project, holding the trap. And the little filter paper here has either a sample of our synthetic pheromone or a virgin female tethered inside. When we put out the natural pheromone, we put out 14 micrograms in 3/10 of a cc of olive oil. That's in the open field. So you see, you really don't need very much of this compound. And actually, now we can do much, much better than the females with our own trapping experiments. Now this is the kind of data that you get. I'm sure this can't be read in most of the room. This column is simply European corn borer males. This column is red-banded leaf roller males. And the one compound that I want to call attention to here is the top one, the Z11 tetradecynyl acetate, which is the pheromone. In these experiments, which are incidentally controlled from the start by the statistics department here, you get 185 European corn borer males and 54 red-banded leaf roller males. Now there are other combinations of compounds that will attract these, and we'll say a little bit about some of them later. But that's the typical kind of data that we get. Now this introduces one of the problems that we get into in the field, which I mentioned. The lower axis here is date, going from July 21 through August 10. And what we were doing here was comparing the synthetic pheromone dashed lines with the virgin females. We wanted to make sure that we peaked at the same points that they peaked, and in fact we do. There was a big flight about the 21st. Actually, it's terminating between the 21st and the 25th. There's another big flight that comes in very early in August, and you can see that we're doing a little better than the females, but we're corresponding exactly to their curve in the field. Now, we've known for a long time that there was something that was eluding us, because we always catch red-banded leaf rollers and European corn borers together, and in fact we get oblique-banded leaf rollers too when they're flying. But if you put out a virgin female corn borer, she gets only corn borer males. And if you put out a leaf roller female, she gets only leaf roller females. And that really has been something of a headache. Even if you put them right side by side, the traps right next to each other, the males sort themselves out. And so the females of those species know something that we didn't know, and we could not do that well. Now, this slide shows concentration effect problems. For the red-banded leaf roller, as you increase in this direction, the concentration of the synthetic pheromone in the air, you see that there's a broad maximum out here someplace, but it's sort of ill-defined. With the corn borers, they're much fussier. Their maximum comes very early, and if you come out here too far, you're dead. And that was one of the early problems that we had with field testing. Here, with the oblique-banded leaf roller, there is, again, a fairly sharply defined maximum, but it's at much higher concentrations of the compound. So that's one of the things that differentiates the insects using this particular pheromone system. Now, every once in a while you run across some circumstantial evidence which is significant. I believe it was Thoreau who referred to the example of the trout in the milk. Sometimes things are very, very suspicious. We did an interesting experiment in which we put out the cis pheromone, that is the natural pheromone, the inhibitor of the natural pheromone, and a 1-to-1 mixture. Actually, these two should be switched. Naphasia should be here, and Ostrania should be here. What happens is that with the corn borer, you get only with the corn borer males, you get them only with the cis compound. If you put out the trans, you get none, and if you put out the cis-trans mixture, you get none. Now that's significant. This is the data that shows there's inhibition. Even though you put out as much cis here as you did here, you get no corn borer males. That's a clear indication that trans is an inhibitor and shuts off the response. Now, with the Naphasia species, you find the trans attracting. that is suggestive that this is their natural pheromone. With the Astrainia species, you find them attracted to the one-to-one mixture, which just blows your mind. You know, how does the insect know a one-to-one mixture? Well, okay, you try 60-40 one way and 60-40 the other. You still catch moths, but you catch fewer. The darn thing is tuned on the 50-50 mixture, and the maximum is there. It falls off on both sides. Well, that was a clue too, but we were still a little slow on withdrawal. Now, one of the things that a chemist would like to do is play games on natural systems, and I'm sure all of you have seen this television ad that says it's not nice to play tricks on Mother Nature. Well, it's not. you get caught sometimes. This is the natural pheromone. After the Z double bond, it has 2 carbons. Now, all of the compounds of this sort in nature have an even number of carbon atoms because nature makes it from 2 carbon units, that is acetate units. So we thought, well, let's see if it can tell the difference between 2 carbons and 1 carbon. That's an odd carbon chain. The insect can never have seen this. So why shouldn't we see what it can do? Okay, so we made this compound, and we thought, well, just for the heck of it, we'll make the E isomer as well, or the trans compound. Put them out in the field. Neither one of them have any activity at all. Well, fortunately, the microphysiologist came to our rescue there because it was found that this compound fired cell B in the insect brain, in the receptor system, and this compound fired cell A. So the obvious thing to do is put out a mixture of them. You put out a mixture of these two, and you get moths. This is the data with 14 carbon compound. You get 185 males with the natural pheromone. You get now with the unnatural compound, the cis essentially 0. This is not statistically significant, not statistically different from 0 rather. The trans gives you about the same or actually a little lower numbers. But if you put out a one-to-one mixture, you're almost as good as the natural pheromone. Okay, so you have a synonym here based on an understanding of microphysiology of the system. But at this stage, you begin to wise up, and you understand what you should have understood right along. Remember that in the synthesis of the Z isomer, there was always a few percent of the trans. Now, the experiments on inhibition were carried out this way. As the percent of the E isomer was increased, the number of males decreased. And then the thing is to be exact about it and to go back and do this, not starting from something that contains 7% E in the beginning, but to go back to pure Z. So if we start from 0, actually you see this curve starts from 7% E. Start from 0 and increase the percent E. You get a very dramatic result with the number of males trapped, which goes like this. The European horn borer males like to have 4% E in their Z. Well, this is the European corn borer. For the red-banded leaf roller, it goes like this. That peak is about 12%. It's just fortuitous that the synthesis gave 7%, which is right there, and just happens to be on the intersection of these two curves. So you get inhibition with both of these as you add the trans to it, but particularly with the European corn borer. Now this turns out to be an extremely interesting thing, because you start to extend this curve on down. You already know that the pure E, that is the 100% E, is the pheromone for the Nephasia species. That presumably will work better with a little cis in it. The Austrainia species has a maximum in here at 50%, And what one is developing is a tuned system based on the percent E and Z. It is a speciation mechanism in these insects. And this is an extremely important biological fact, a very basic biological fact. These insects are tuned to cis-trans ratios, to Z to E ratios. And now we can go back and put 4% out and get only European corn borers. We can go out with 12% and get only red-banded leaf rollers. Actually, you get unpopular when you do these experiments because the numbers change radically here. This number might be something like 100. This number would be something like 400. Now, you're really getting pretty good. And at the stage when you're going out with this lure, the 4% E and Z, all of a sudden the other people who are doing corn borer experiments don't find any moths in their trap. We're getting all. So we have to go a little further afield to do these tests now. But this is a very dramatic work for these. And the inhibition then is, of course, quite real. Now this shows how we got into this. Test 1 is with the pure Z isomer. We were down to 20 corn borers and 0 red-banded leaf rollers. Well, that was bad news because we had put out the old mixture that had 7% E in the Z, and we got 68 corn borers and 103 red-banded leaf rollers. Of course, you get that kind of data, and you say, well, that's no good. Somebody moved. You go out and immediately do it again. The second test gave 46 corn borers with pure Z, 0 red-banded leaf rollers. There's no way out. You don't catch red-banded leaf rollers with pure Z. Again, the original ZE mixture gave 103 and 24. The totals for this test, European corn borer 66, red-banded leaf rollers 0 with the pure Z, with the ZE mixture 171 and 127 for the two species. So the pheromone of the red-banded leaf roller was completely misinterpreted in the original thing because the pure Z isomer is just not effective. It is a cis-trans mixture. Neither pure Z or pure E is effective. You want 12% E in the Z. This shows actual plots. This is the maximum for the European corn borer. This is the maximum for the red-banded leaf roller. And the schematic plot, again, the corn borer, the leaf roller, the smartweed borer, the European corn borer of New York. And I think that this summer well, I know that right now we're putting out traps with intermediate concentrations looking for other insects, and we have sort of a you dial an insect kind of means of tracking these. But it is a beautiful thing in terms of understanding speciation and evolution in this type of insect. It is also a fundamental observation for understanding pheromone reception in many species. Now this brings us to a practical application of all of this. Morten Barosa at Beltsville formulated this for us. We start with some 12 to 20 mesh cork granules and impregnate on them the anti-pheromone, the pheromone inhibitor. We put on about 7% of the trans isomer, and we put it in paraffin, in solvent, take off the solvent, leaving the anti-pheromone embedded in paraffin on the cork granules, and then we put these cork granules around the field, protect them. And the cork granules tested in very large fields, 400-acre fields, gave about 90% reduction in the efficiency of mating of virgin females. That's a pretty big gain. You would like to know, though, whether you're actually inhibiting the reduction of new corn borers, and there's a way to get at that. This slide doesn't look terribly dramatic, but let me tell you what it is. If you take 4 cages of European corn borers, each containing 100 males, 100 females, and you put in 4 strips of wax paper, the females like to lay their egg deposits on wax paper for reasons which are best known to them, but it works like a charm. In 2 of these cages, we do nothing. 2 of them we treat with a couple of the cork granules, just a couple of minute cork granules. And you can see the results on the left. These little black dots are all egg deposits. Over here, the little black dots, with the exception these three and this one and that one are all dust specks on the slide. It really is an unbelievable control in terms of reducing the efficiency of reproduction. So one has now a really radically new method of turning off the insect by understanding his physiology well enough to simply go in with an inhibiting compound, which is really an integral part of the pheromone system in this species, and this is a very nice practical way of controlling corn borers. Now, you might ask, well, why aren't people using this? And the answer is, well, you know, traditionally you use pounds or gallons of something per field. We actually just distribute a few grams around the outside of the field. I think that 400-acre field was treated with less than 100 grams of the anti-pheromone, which is just nothing. You know, that's about a quarter of a pound of the stuff. First of all, there's no way for anybody to make money on this, and there is the threat of economic dislocation. So there are many problems with this kind of control. Furthermore, there are other insects that have to be controlled, like the rootworm, species like that. So one needs some more work before this actually goes into the field, but the practicality has, I think, been demonstrated. Well, this work's been a lot of fun. It has led us to some basic discoveries in microphysiology and physiology generally, to basic understanding in biology, and even to something that may someday be quite practical in Iowa fields. So it's a good place to stop. Maybe we can shut off that topic. We can shut that off. I'd be glad to answer any questions I can, if anybody has questions.
Are these insects very closely related? Are they in the same subfamily?
Yes, they're quite closely related. The similarity in their pheromone systems, I think, gives you a very nice picture of just how closely related they are.
Well, the point was, this is obvious, but were they classified on other morphological grounds earlier, independently of this?
They are closely related. Beyond that, I'm not biologist enough to speak.
If this were put into a controlled procedure, you do have some variation among individuals. Have you any idea how this is inherited, so that they could build up a resistance or have all sorts of other little mechanisms for reacting to different levels or different ratios, and you would be selecting for something quite different from the average?
As I understand it, I think I've got the little blighter, but it wouldn't be the first time they proved me wrong. Basically, in two dimensions, as long as he sticks to two compounds, I've got him, because he's so close with 4% to 0 that he doesn't have any room to move in that direction, and if he moves in the other direction, he turns into another species. That is, he gets into the hair of the red-banded leaf roller. Okay? Now, but he may have another dimension to that. Instead of being a two-dimensional plot, it may be a three-dimensional plot, and I may be looking for something that I don't know anything about yet. That is, there may be a third compound or a fourth compound that give him new directions in which to move. And that, frankly, I worry about.
Let's see, one other compound tells them where food is.
Quite. If you look around the fields in Iowa, the corn borers sit in two kinds of grasses, smartweed and foxtail. And that's no accident. I think the plants are giving off an odor that is a swarming or congregation pheromone for the insects. And if I had some bioassay, I would immediately go after that. The symbiosis between plants and insects is very important. The corn rootworm, the one that gets in the ear of corn, apparently works off a pheromone that comes from the developing corn silk. And you can take the corn silk out and put it in a cage around the corner from these little rootworms, and they will go right for that silk. So we're after that one. That one I think we can do the bioassay on, so we can get it. I'm sure that there are other pheromones, perhaps even alarm. In the moths, there would be no need for feeding pheromone, but probably they also have a swarming pheromone that they can secrete. Most insects do, many insects do, at least flying insects. I'm sure there are lots of pheromones. In the insect world, where pheromones have been studied a little longer, there are now 10 words recognized in the pheromone vocabulary. There's a pheromone that says, "I'm dead, bury me." That's kind of a cute one. It's a long chain diamine. The trick is that an ant has to recognize how a dead ant from an ant that's still hibernating. They look just about the same. So he goes up and snips them. And if it's giving off this diamine, he takes it out on the refuse heap. Now what is funny is to watch one of these ants that is live and has been treated with this compound. Because he keeps crawling down into the anthill, and the other ants keep dragging him right down. These, in the ant and bee things, they're very complicated problems, which are poorly understood.
The question is, you mentioned 100 molecules for CC. If you calculate the area of the receptor on the body compared to a cubic centimeter or square centimeter, that's very small. And if one ought to be able to calculate statistics just how many times a molecule in a container would bombard the antenna at any point, and the chance of getting into the receptor is pretty darn small. I suppose you can calculate this. So what all this means is there should be a time lag between the time you put the bug in and between the time one molecule happens to hit. Or in your case, it has to be a Z molecule and an E molecule all simultaneously. And this seems like statistically this never should happen.
It does not work out if you do the calculation. If you do the calculation using an estimate of the total surface area of the moth, much less that one little organelle, the whole moth, at that concentration of molecules, the mean free path of the molecules is such they should never hit an insect. And so the insect knows something again that we don't. And I suspect those little blades on the antenna are the secret. I think they flutter. And that's probably an amplification system. That is, they keep air circulating over those at a very rapid rate, and it's driving it right up over those organelles. So I think that it's not just a static air calculation that you need. The insect is improving on that somehow, but I don't know.
How about the ZD ratio now? There must be a time lag between a Z molecule and E molecule.
Well, with the corn borer, I know a little bit. What I know about the corn borer is that when he senses cis, he will fly. And he'll go upwind until he finds out whether it's a leaf roller or a corn borer. Now the red-banded leaf roller won't fly on pure cis, but I think that he will respond to trans, or he will sit until he starts to get a little of both. I don't know how he works exactly, but I do know that with pure cis you don't catch leaf rollers. So there are problems. I don't know how they get started. They need a higher concentration than corn borer. Remember those concentration slides? They have a much broader maximum and very much further out. So it may be that is in part caused by the need to get some trans on the antenna before they become sensitive to the cis. Well,
How are these ratios generated? How does the female generate specific?
God only knows, as far as I'm concerned. She doesn't generate enough for me to detect after dealing with 250,000 like her. And a factor of 2 or 4 is not going to change our chances significantly. We needed a couple of orders of magnitude to do any better. I don't know how she does that. She may have a catalase or something that changes the cis-trans ratio. In fact, we've come to suspect that she doesn't make the acetates the way you and I would make them if we were insects. She starts, I think, from the methyl ketone and uses a Baeyer biligerase to put in the oxygen. So, their thinking is very foreign to ours. So actually, turns out to be methyl ketones. Apparently, the methyl ketones related to the acetate. So one could, in principle, go back and look at those enzyme systems. But that's the sort of thing that you'd like to sell to somebody else, and hate to do it for